So today we're going to work on a new concept called the quadratic relation that we kind of talked about the previous day. And more specifically, we're going to talk about the graph of that relation called a parabola. And our parabola in this case for today is going to look something like this. Y is equal to ax squared plus k. All right, we're going to identify what the a value is and what the k value is, and we're going to try and identify what it actually does to the graph of the parabola, what the a value does and what the k value does. So now what I want you to do is I want you to go to desmos.com or simply watch my video as a demonstration. So we're going to go to desmos.com, and in Desmos, we're going to start by typing in y is equal to x squared, and then we're eventually going to get this equation and use it to test to see what happens with our k values of our graphs. So now just switch over to Desmos, keep this sheet in front of you, and watch the demonstration or follow along. You'll notice that you have a table of values to the right of your screen here, so the right of your work there. That table of values is designed to help us understand what the base values of our graph are. So we are going to go and create a table of values for the x and the y for our graph. Now, Desmos doesn't understand that what y is. You actually have to tell it what y is going to turn into. And in this case, we actually have to say that y is equal to x squared. So what that's going to allow us to do is it's going to allow us to see all of the points, all of the key points for this parabola. The only key point that we can see right now is this point here, 0, 0, where our vertex is. And our axis of symmetry is our x value, also known as x equals 0. The optimal value is going to be y equals 0. Okay? Now, here's how you get Desmos to go and automatically generate and calculate all of the values that we need for x. So we're going to go from -3, and you'll notice -3 turns into x squared, right? And then x squared is calculated to be 9, which is just -3 times -3. Now, in order to get Desmos to calculate the rest of the points from -3 to +3, all we're going to do is we're going to take -3 and change -3 on the next line to be -2. And then Desmos understands that we have a pattern that we need to follow. We start from -3 and we're adding 1 to each one of our x's. And you'll see when you hit enter, you click on it, you hit enter for each one of the points afterwards, you get all of the values. And you'll notice that all of those points are now showing up on our graph for y is equal to x squared. So this is x, and then this value here in this second column represents the y value that is represented here. Now, let's go and take a look at our problem once again. Remember, we're going to start with y is equal to x squared plus k. We're going to type that in. And what I want you to understand is we're going to add this thing called a slider. And a slider is very powerful in the sense that we can visually see what happens when we change the values of k dynamically. Okay? So if I go and click this slider here, this goes and automatically shows me that when k is equal to 1, we see that our graph has actually moved up 1. And I can tell that from looking at my vertex of each parabola. So the first vertex is 0, 0. But the next vertex translates up 1, or you could say shifts up 1, or moves up 1 unit. Does that make sense? Now, let's go and test our hypothesis. So imagine that we let k be, instead of 1, let's make it 5, right? So if it's 5, oh boy, if it's 5, if k is 5, you'll notice that the graph, its vertex compared to the original graph, is at 0, 5. Huh, that's interesting. So the vertex of the first graph is always 0, 0, but the second graph is always 0k. So the graph goes up k units, and the vertex is now 0k. All right? So the original vertex for our first graph, for the base graph, the vertex v is 0, 0. There we go. So the vertex for the base graph of y is equal to x squared is always 0, 0. But when we're talking about, when we're literally talking about the other graphs where we add some value to it, a positive value, the vertex shifts up, which means all of the points of the graph shift up. That's why it looks congruent to the original graph. Okay? So its vertex is now 0k. So now, what do you think would happen if we let k be negative? So in this case, we let k be negative, right? So now, if k is negative, there's our vertex. K is negative 5.5. Oh, wow. The vertex is just still 0k, but the k value is negative. So let's go back to our sheet and then write out some examples as to what you would see. Think about what we did. We had our first graph for this thing here. So if k was positive, an example of our graph was y is equal to x squared plus 5, right? And its vertex was 0, 5, right? So remember, 0, 5, there's a matching number there, right? And you'll notice if k is positive 5, then the vertex has a 5 in the y spot of the vertex. So that means our graph shifts up, shifts k units up, right? Now, if we had a graph that looked like this, y is equal to x squared minus, say, 3. Our equation for our vertex is going to be 0, negative 3. And what that means is our graph shifts down, shifts k units down. Now, you remember from our graph when we went from, say, x is negative 3 to, we basically use the calculator to go and do this table, right, for y is equal to x squared, right? In order to calculate this, what we literally have to do is start by going y is equal to, well, let's say I wanted to find if x is equal to negative 3, right? What I would actually have to do is actually start with y is equal to x squared, and then we just substitute negative 3 squared and go y is equal to negative 3 times negative 3 is 9, and then we would put our answer in as 9 here, and we do the same for the rest of these. So you got 9, 4, 1, 0, 1, 4, and 9. All of those values are key values to the base graph for y is equal to x squared. So what we're going to do is we're going to take a moment. We're going to graph that on this graph by hand. So start with negative 3, 9, plot it. Now for negative 3, 9, you're going to go back 3, 1, 2, 3, and then go up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then plot your point. And we'll do the same for all of the points down to the vertex, down to the lowest point. And now what's interesting is, remember we studied that concept called the axis of symmetry, right? The axis of symmetry actually goes through the vertex of every parabola, right? Which means that I can take my graph and mirror the points directly across from the mirror line, also known as the axis of symmetry. So it makes this very easy for us to graph these parabolas. Okay, so now we have our basic graph matched and pointed out properly. So the key idea is, if I have x squared minus a number, the graph shifts down. If I have a graph of x squared plus a number, my graph shifts up. That's all it does. So let's take a look at this set of problems right here. So we're going to graph y is equal to x squared, right? So we got y is equal to x squared, which is our basic graph for our problem. So now we want to see what y is equal to x squared plus 4 is. So the key is, you just got to remember that all the points move up or down from the base graph. So let's do that, shall we? All right. So let's say that I wanted to go and take a look at y is equal to x squared plus 4. So I'm going to circle that in blue, and we're going to use blue to graph that. Okay, so if I look at the original graph and I'm looking at the vertex, right, that means I have to go up 4 points. 1, 2, 3, 4. So that is where my point is for the vertex. And then what I can do is I can just move up all of the other points exactly 4 spots. So take this point and we move it up to here. This point, move it up to here. This point, move it up to there. And then when you've got half of your graph, you can go and just mirror the points to the other side of the graph, and then connect your lines, your curve. And quietly label your graph to be y is equal to x squared plus 4. You'll notice that every graph I always tend to put arrows at the end to signify that the graphs will move on forever. Now my question for you is this: if I have y is equal to x squared minus 7, which I'm going to graph in black here, right? What does that mean? It means that from the base graph of y is equal to x squared, which is here, right, which we've plotted using these points here, basically all we're doing is moving down all of the points exactly 7 spots below to get something like this. So we're just going to count 7 spots down. 1, 2, 3, 4, 5, 6, 7 spots. There's our point. We're going to write our point in. So we have our first point, and then we do the rest. Just move them down. And there are our points, and here's our final graph. And there we go. Now, we've labeled all the graph with the corresponding equations. Let's move on to the next concept. The key idea is, if we have x squared plus a number, we move it up. If we have x squared minus a number, we move it down. So now, what happens when we have an equation that looks like this? Y is equal to ax squared. What the heck actually happens? So now we are going to go and imagine that we have our base graph of y is equal to x squared. Make sure you label your graph and you identify all the key points. So now we have to understand what's actually happening with our graph. So let's go and look at this concept in Desmos. So we're going to take a look at y is equal to ax squared. Now, when we go and type in ax squared, we get this nice slider. Now we're going to click the slider, and it's going to give us something interesting. It's going to give us the base graph of y is equal to x squared. So let me just type that in so we have that. Y is equal to x squared. Now, the blue graph is our original graph, and then this new graph with a is equal to 1 is our red graph, which is going to sit underneath our blue graph here. So now, what happens when we have an a value that is bigger than 1? So what actually happens? So if we go and choose our a value to be bigger than 1, so let's say it's 4, right? Basically, what happens is our graph gets skinnier, all right? And because it gets skinnier, we call it stretched. So essentially, when we take a look at our graph, if we just ignore the sign, the graph gets stretched, gets pulled taut, gets smaller than the original base graph of y is equal to x squared. So when I go and stretch my values, I end up with a skinnier graph, okay? We call this compressed. Not compressed, stretched in a curve, okay? So we say that the curve is stretched in this case. Now, my question for you is, ignoring the sign, what would happen if our value of a was between 0 and 1? So let's go and change this to say 0.5. As I get closer and closer to 0, my graph gets closer, gets fatter and fatter, right? We say, in this case, so when we basically have our value of a being bigger than 0 but less than 1, we end up having our graph being compressed. As long as we ignore the sign, the graph is compressed by a factor of a. All right, now, if we take a look at the stretch thing, we say that the graph is stretched by a factor of a. So here's an example. Suppose I am looking at y is equal to x squared. Y is equal to 2x squared, right? So we have that black graph there. When we look at that black graph compared to y is equal to x squared, it's skinnier. So you could literally say that this graph is stretched by a factor of 2. So essentially what we're doing is we're multiplying each of the numbers for the y values of each graph by a factor of 2. Okay, now if we do the same for this type of equation, y is equal to let's say 0.5x squared. Our graph is going to be not stretched, but this time it's flattened. So now it's compressed by a factor of 0.5. So all we're doing is taking the 0.5 and multiplying by each of the y values to get those things. All right? So it's very similar to what we did before, and that's it. Okay? The only thing that we have left to look at is what happens when we have a negative value. Ready? So here's what I want you to do. I want you to watch the red graph, and you'll notice if I have a negative value, all of what we did here still applies, but if it's negative, our graph opens down. If our graph is positive, if the a value is positive, then we know our graph opens up. That's all you need to know. Okay? All right, back to the lesson. All right, so coming back from Desmos, here's some of the things that we understood. If a was positive, then we were going to say that the graph opens up. Now, if the a value is negative, then the graph opens down. So let's give you two examples. So for an example, you would have y is equal to 2x squared. And that opens up because its value 2 sitting in front of the x in front of the x squared term is positive. Now, for the second one where a is negative, we'd have something that looks like this. How about this? Y is equal to negative 3x squared. So this one opens down because it's sad, it's negative. This one is positive, so it opens up. It's positive. It's smile. You can think of this as smiley face and then negative face. All right, now let's go over the skinny concept. A graph is skinny. That means the value, ignoring the sign, is greater than 1. And we say that it is stretched. So here is an example of a stretched graph. So you'd have y is equal to 5.5 x squared. Or another example would be y is equal to, say, negative 5.6 x squared. Now, as long as I ignore the sign, one of them opens up, right? But its stretch is 5.5, a factor of 5.5. But this one here is a stretch factor of negative 5.6. But the negative means it opens down, but the 5.6, because it's greater than 1, tells us that this graph is stretched. Now, for this next one, we say a graph is fat or flatter, right? So it gets squashed. Then the graph is described as compressed. And you could say an example of this would be y is equal to 0.5 x squared, or you could come up with y is equal to negative 0.1 x squared. This first one is positive, it's opening up, but its stretch factor is 0.5, so that means it's getting flattened. And then if you look here, this one is opening down, but its value of a is 0.1. And because it's 0.1, it's less than 1, it's still compressed. But its compression factor is 0.1. So the next thing that we're going to do is we're going to take a moment and graph y equals x squared. We've already done y equals x squared. We did that one in red, didn't we? So the next one that we got to do is we got to do y is equal to 3x squared. So let's go over how 3x squared would work. So if I wanted to use 3x squared, you think of what happened when you calculated x squared, right? And to go from x squared to 3x squared, all we're going to do is times everything by 3. So that means we're going to take 9 and times it by 3. So 9 times 3 gives us, oh, look at that, 27. And then 4 times 3 gives us, ooh, look at that, not 27, but 12. And then 1 times 3 gives us 3. 0 times 3 gives us 0. What was this? 1 times 3 is 3. Then 4 times 3 is 12. And then again, one more time, 27. Now, we only have a few points that we can work with here. So for this one here, the first point I'm always going to start with is 0, 0, because it's the easiest thing to draw. I'm going to draw this in blue. So y is equal to 3x squared. We start at 0, 0. We go over to position 1. In this case, position 1 and 1. Instead of 1 and 1, we're going 1 to 3. So now we go over 1 and then we go up exactly 3 spots, right? And then for 2, we'd have to go, instead of 4, we'd have to go all the way to 12, which is way off of this graph. So we'll just stop there. We've got our basic graph. And now all we do is connect the dots. And this is our graph of y is equal to 3x squared. And all it's done is it's just stretched all of the x values by a factor of 3. We just took, instead of y being 1, y is now 3. Instead of y being 4, y is now 12. That's literally what we did. So now let's take a look at y is equal to negative x squared. So for y is equal to negative x squared, right? What we're going to do is we go and draw it. You go and draw it, y equals negative x squared, and some craziness ensues. So let me just erase all this, and we'll continue. So now let's consider y is equal to x squared being changed into y is equal to negative x squared. So negative x squared is kind of like saying the following. Instead of y is equal to negative x squared, we can write that as y is equal to negative 1x squared. So essentially what we're doing is we're changing it by multiplying each of these numbers by negative 1. So 1 times negative 9 is just negative 9, and so on. So essentially the a value in front of the x squared term just multiplies all of the y values from the original graph. So now when we go and graph our y is equal to negative x squared, our y is equal to negative x squared looks something like this. So we start at 0, 0 like before, but for let's go 1, we normally would go 1 to 1, but now we've got 1 to negative 1. So that means we've got this point and this point. Then we also have negative 4 for 2 and negative 2. And then we just connect the dots. So now what would y is equal to negative 0.25 squared look like? When we go back to our original set of calculations, so we have y is equal to x squared turns into y is equal to negative 0.5 x squared, right? So all we're going to do is just going to multiply everything by negative 0.5. All right, so 9 times negative 0.5 gives us negative 4.5. And so on, okay? And we're going to take all those points and just graph them. Now, imagine we're going to use, I think we're going to use black for this one. So for this one, we're going to use black. So we'll just plot all our points. So 0, 0 again, but then 1 to 0.5, and then 2 to negative 2. And then same for the other side. And we are done. All right, so in order to describe this next set of problems, we have to figure out how all the points have changed. So here's how we do this on our graph. So let's say that we've got this graph of y is equal to negative 2x squared plus 8, right? The key idea for reading the changes is this. You read from left to right. So here it is. So you're reading the stuff from left to right. So if I have y is equal to negative 2x squared plus 8, you're going to say the following. First of all, when we're reading from left to right, we notice the minus sign that's on the x squared term. So this means it opens down. For the number after the minus sign, you check. It's a 2, so that means it's stretched by 2. In other words, we're just multiplying by 2. And finally, the third thing here tells us that we move our final graph up by 8. All right, now let's create our base graph and then show all the transitions from number 1 down to 8. Okay. So based on our original graph, we get this for y equals x squared. Now, in order to change it into y is equal to this thing, the minus 2x squared, so that represents the stretch, we have to take y is equal to x squared, and we're going to turn it into negative 2x squared. So in order to do that, all we got to do is times each of these by minus 2. So 9 times minus 2 gives us negative 18. and then -8, -2, 0, -1, oh, -2 again, -8, and -18. So all we have to do now is draw the graph with an x is -3 and then -18, a -2 and -8, and so on. Now, there's not enough space on our graph, so we can only draw a couple of points. So I'm actually going to draw these in blue to start. So we've got this point, 0, 0. Then if you look at the next point, -1, we're supposed to have -2. So we got this, right? And then for +1, we're supposed to be at there, okay? And then the rest of the graph is off of the chart. So let's just draw our upside down chart, right? So this is y is equal to -2x squared. So our final graph is going to be pushed up with pushed up by 8. So we literally take this final graph here and move all the points up 8 points. 1, 2. So I'm going to move the vertex up 8 points. 1, 2, 3, 4, 5, 6, 7, 8. So there's our vertex. And I move up all the other points that I see. So there's the other point. There's the other point. And then the rest looks like this. So there is our upside down and stretched parabola, where it's y is equal to -2x squared plus 8. And you're done. That's it, right? You can also sketch it. So if I ever ask you to sketch it without points, all you're going to do is just find where the vertex should be and then draw the graph just a little skinnier than the original. But if I ever ask you to show me all the points, you got to flip it first and stretch, which is the yellow part there. And then you move your final spot up. Okay? All right. All right, so for this next problem, we have y is equal to -0.5x squared minus 2. So remember, we're reading from left to right. Y is equal to -0.5 x squared minus 2. Okay, so -0.5 x squared minus 2. So we remember we need to read from left to right. So here's the description. You can say that because it has a negative sign in front, the negative sign in front tells us it opens down. Number 2, you can tell me if it's a stretch or compression by looking at this part here. You're going to say there is a compression. Or it's squashed flat, right? And then finally, it's a compression, and you're going to say by 0.5. And then finally, your last description tells us whether it opens up, whether it moves up or down. And this one moves down 2. All right, so now let's go and do the calculation for this. So remember, in order to change our original graph, y is equal to x squared into this portion of our graph, what we have to do right away is we have to basically change our number to, what was it, -0.5 x squared. And in order to do that, we have to multiply 9 by -0.5. So you got to get -4.5 and so on. And then you take those points and match them with the x's and graph. And now that I've got that, what this will allow me to do is, now that I've got my flipped graph with its stretch properly, now we can go and move our graph down 2 points. And all we do is take all the points from our last graph that we just created and move the points down. And here we go. So this point, the vertex goes down 2 points. There's another, and there's another. Boom. And this point moves down 2 points. And now we graph our final thing. And there is our final graph. Y is equal to negative 0.5 x squared minus 2. And I guess this black one was y is equal to negative 0.5 x squared. All right, and we're done. Okay, we're almost done here. Just 2 more sections. All right, so here's a possible graph that we need to do. So for this graph, all we have to do is graph the relation and then find our equation for our graph by using this y is equal to ax plus k form. And the key idea is to graph the points on the graph and then find the vertex, use the vertex to help us figure out what our k value is. And then we have to find the a value by plugging in one of those points. So in this case, we're going to do the math version of it, and then I'm going to show you how to do the final version. That just uses a really cool feature about quadratic. What we need to do is we need to make sure that we graph all the points. So now plotting our points, we have something that looks like this. So based on this, we're going to get a graph that looks like this. And you'll notice that the vertex is at 0, 3. Now, I told you that with our basic equations, right, that 3 is very important in this basic equation. So that means in our original equation, y is equal to ax squared plus k, that this is k. So k is equal to 3. So it's always k comes from this vertex every single time. Now, in order to find the a value, what you have to do is you have to literally look for this. Go over 1 and find out how far it goes down from the 1 over and down. In this case, it's minus 2 from the vertex. So that means, in this case, a is minus 2 down from the vertex. So a is equal to minus 2. So the final equation is equal to y is equal to negative 2x squared. Let's, I'll actually be nice about this. I'll color code it. Negative 2x squared plus 3. And there is our answer for our final graph. And there we go.